Chapter 6 in Thermodynamics. Gas power cycle. The compression ratio of an air standard Otto cycle is 8.5. Prior to the isentropic compression process, there is 100 kilopascals, 35 degrees Celsius, 600 cubic centimeter. The temperature at the end of the isentropic expansion process is 800 Kelvin. Using specific heat values at room temperature, determine the highest temperature and pressure in the cycle, the amount of heat transferred in kilojoules, the thermal efficiency, and the mean effective pressure. Now let's analyze our given. With our compression ratio at 8.5, our initial pressure at 100 kilopascals, our volume at 600 cubic centimeter, our T sub 4 at 800 Kelvin, our T sub 1 at 35 degrees Celsius, and we're tasked to find the highest temperature and pressure, or T sub 3 and P sub 3, our Qin, our thermal efficiency, and our MEP. Now we can find our highest temperature and pressure using the equations seen in the presentation, but we're missing our values of T sub 2 and P sub 2, but we can calculate that starting off with our temperature at our second state using the equation T sub 1 multiplied by B sub 1 all over B sub 2 raised to K minus 5. Now we know that B sub 1 over B sub 2 is equal to our compression ratio, which is 8.5. Now let's just integrate our values, adding 273.15 to our degree Celsius to change that into Kelvin. And our T sub 2 will be 725.32 Kelvin. Now let's solve for our P sub 2, which will be P sub 1 multiplied by T sub 2 divided by T sub 1, and our V sub 1 all over V sub 2. And we'll have 100 kilopascals multiplied by 725.32 Kelvin all over 308 Kelvin multiplied by our compression ratio, or V sub 1 over V sub 2. And we'll have our P sub 2 at 2001.7 kilopascals. Now that we have our values, we can solve for our highest pressure and our highest temperature. With T sub 3 will be equal to our T sub 4, or 800 Kelvin, P sub 4 divided by B sub 3, or our compression ratio also, raised to our specific heat ratio of 1.4 minus 1. And we'll have our value of 1883.03. And that's our highest temperature. Now our highest pressure at P sub 2 times T sub 3 all over T sub 2. And since we can see that volume is constant at state 2 and state 3, we can say that it is equal to 1. Now we'll have our highest pressure at 5,196.69 kilopascals. Now let's solve for our Qn, and we can get that by multiplying our mass to our change of initial energy in state 3 and to state 2. Or simply, our mass multiplied by our constant volume and the change in temperature in state 3 and state 2. Now we can have our mass using the ideal gas equation, manipulating that so that M is isolated on one side. We'll have on the other side P sub 1 multiplied by our volume all over our gas constant and our initial temperature. Inputting our values, we'll have 100 kPa, 600 cubic centimeter. Changing that into meter, we'll have 1 over 100 centimeter raised to 3 all over our gas constant for air at room temperature 0.287 kilopascals cubic meter divided by kilogram Kelvin, and our initial temperature at 308 Kelvin. And we'll be left with 6.76 times 10 raised to negative 4 kilograms. Now we can solve for our Qn with our mass at 6.76 times 10 raised to negative 4 kilograms, our constant volume for air at 0.718 kilojoules per kilogram Kelvin, and the change in temperature in state 3 and state 2, or 1883.03 Kelvin minus 725.32 Kelvin. We'll have our Q sub n at 0.56 kilojoules. Now let's solve for our thermal efficiency using the equation work sub out divided by Q sub in. But we don't have our value for work sub out. And we can get that by subtracting Q sub out minus our Q sub in. Now we don't have our value for Q sub out, but we can solve that by the equation of our mass multiplied by the change in internal energy in our state 4 and our state 1, or simply our mass multiplied by our constant volume and the change in temperature in T sub 4 and T sub 1. Inputting our value that we have earlier of our mass at 6.76 times 10 raised to negative 4 kilogram, and our 0.718 kilojoules per kilogram Kelvin, our constant volume for air, and the change in temperature in state 1 at 308 subtracted 2, or T sub 4 at 800 Kelvin. Calculating that, we'll have 0.24 kilojoules. Now that we have our Q sub out, we can solve for our work sub out. And that will be 0.56 minus 0.24 kilojoules. And we'll have our value of 0.32 kilojoules. Now we can finally solve for our thermal efficiency with 0.32 kilojoules of our work out all over our Qn at 0.56 kilojoules. And we'll have 0.57 multiplied by 100, so we have 57 efficiency. Now lastly, we'll have our map, and we can solve that by our work sub out all over our v sub 1 minus our v sub 2. Now our v minimum is v sub 2. Since looking at our PV diagram, we have v sub 2, or our state 2 at the least value, and we can get that by our Vmax, or our state 1, since it has the highest value in our volume, divided by our compression ratio. Now integrating that into our equation, we'll have work sub out all over v sub 1 multiplied by 1 minus 1 divided by our compression ratio of R. Inputting our values, we'll have 0.32 kilojoules divided by our volume 1, or 600 cubic centimeter, changing that into cubic meter by multiplying it to 1 meter all over 100 centimeter raised to 3, and 1 minus 1 over 8.5. We'll have our value of MEP at 604.44 kilopascals.